Welcome students. We will start with the derivation for moment of resistance for a doubly reinforced section. So as I already mentioned, doubly reinforced section, we have area of steel in tensile zone and also we have area of steel in compression zone. So here if we consider the total bending moment as M, it will be split into two halves, that is M1 and M2. Where M1 is moment that can be developed by balance section without compressive steel. Now this value of M1 is equal to Mr, which is equal to RBD square. So this is the section that can be derived as a singly reinforced section, balanced singly reinforced section. Here the maximum amount of moment that it can resist is Mr, which is equal to RBD square. Now when we have additional moment, that is moment more than Mr, we go for doubly reinforced section, and that is this value M2, that is moment in excess of M1. So here instead of Mr, we are going to use the term as M1. Okay, so moment in excess of M1, that is to be provided by compression steel. Now because we have two M1 and M2, or we have split that bending moment, we have AST, that is total tensile force, also written as AST equal to AST1 plus AST2. Now AST1 is tensile steel corresponding to balance section, that is Mr. So AST1 that is provided is with respect to the value of bending moment M1, and AST2 is with respect to the bending moment M2. Okay, to give you a clear idea, I will just consider a beam section here. Okay, so there is some ASC here and there is AST that is provided. Okay, so when I say there is that moment M1 which is equal to Mr, with respect to this M1 we are going to provide certain amount of I'll take this total as AST1, 3 bars, certain amount. Okay, this is just an example. So this is AST1. Now when it comes to M2, that is the additional moment, we have to provide this, that is AST2 plus the compressive steel, that is ASC, corresponding to moment M2. This is what it means. So total moment is equal to M1 plus M2. Total area of steel in tension will be AST1 plus AST2, and there will be ASC, that is in compression zone. So M1 is regarding AST1, M2 is regarding AST2 plus ASC. Okay, so now we will go ahead with the derivation of Mr. For that we will have to again consider the stress diagram that we did earlier. So again referring to the stress diagram, we will take moment at tensile force T. Okay, so we will be taking moment at this particular point. So what it will be? It will be force C1 into this lever arm plus C2 into lever arm. Earlier case it was only C into lever arm, but now we have two compressive forces, that is C1 and C2. So if you take moment at point T, it will be C1 into lever arm plus C2 into lever arm. Okay, so by taking moment at T, we can write this M equal to C1 into lever arm plus C2 into lever arm. Now what is the value of C1? It is same, again half base into the width, height you can consider, base into height into the value or stress C, and lever arm is D minus N by 3. So this is C, this is lever arm. This is the same value what we have done for singly reinforced section. Similarly, what will be the value of C2? C2 is nothing but MC, we have to consider the modular ratio, into ASC. The stress here is C dash. Okay, we used to consider T. Similarly, we have considered C2 now. C2 is MC, modular ratio, into area of compression steel into the compressive stress. And the lever arm is D minus DC. I will explain, or I will consider the diagram and check. So for C1 it is this lever arm, that is D minus N by 3. This is D minus N by 3. For C2 it is DC. So it is D minus DC. Now as we add this C2, we will have to also consider the concrete that is removed. So we will have to consider minus ASC It is the same way that we have done in the previous case. We will have to consider or minus the amount of concrete, that is ASC into D minus DC into C dash. Same place. Only thing, modular ratio will not come into picture, as this is the concrete. As this is the steel, we have considered the modular ratio. So we add the steel that is in the compression zone and we minus the amount of concrete of the same area. Okay, all the other things remain the same. Now this we can simplify and write it as dNc by 2 into D minus N by 3 plus ASC C dash D minus DC MC minus 1. Again, if you simplify, or we substitute the value of N is equal to KD, and if we take DC equal to A times D, we will be able to write the value of M, or equation for M, as half into we can write this as half into D into C into KD, D minus KD by 3. I am just substituting the value of N here, ASC into C dash, D minus DC, we have written it as E times D into MC minus 1. Okay, so again I can write this as half into J. If I take this D common out, it will be 1 minus K by 3. So I can write this as J into, I can write this as again K. We have C and remaining terms are BD square plus ASC. This remains the same. We cannot simplify this any further. MC minus 1. So this can be again written as RBD square plus ASC into C dash. I can take this D common. It will be 1 minus E into MC minus 1. Okay. So as we said, M is nothing but M1 plus M2, where this is M1 and the remaining part is M2. So M1 is nothing but MR, which is equal to RBD square, which is corresponding to the balanced singly reinforced section. Okay, so this is the equation for M, final equation for M. Now, from the first derivation in singly reinforced section, we have derived AST equal to MR upon T into lever arm. So which we write it as MR upon sigma ST into J into D. Okay, we have already done this. So similarly, with respect to M1, which is equal to MR, I can write AST1 is equal to M1 upon sigma ST into J into D. Same concept, if for MR it is AST is equal to MR upon T into lever arm. For M1, I am writing it as AST1 equal to M1 upon sigma ST into J into D. Similarly, I can write equation for AST2, which will be equal to M2 upon T into lever arm, where M2 T will be sigma ST. Now the lever arm for this will be different. This will be D minus DC, because this lever arm is with respect to the force C2. Okay. J into D was with respect to the force C1 in the stress diagram. This was J into D. Now with respect to C2, it is a different lever arm. So I have considered it as D minus DC. So for AST2, we get the equation as M2 upon sigma ST into D minus DC. Now to calculate the value of ASC, that is the amount of steel required in compression steel, we have to equate again the movement of equivalent areas of compressive steel and additional tensile area, that is AST2. So what we are doing, we will just equate this MASC into N minus DC from considering at neutral axis. M into ASC is compressive steel, N minus DC is the distance from the neutral axis. If we take this, we will have to minus the amount of concrete, that is ASC into N minus DC, and equate this to the area of additional steel, that is AST2, and the distance of this from neutral axis is D minus N. So from this equation we can write ASC equal to M into D minus N divided by MC minus 1 N minus DC multiplied by AST2. Only you will have to simplify the above equation and we will get the value of ASC. So from here we will need the equation for AST1, AST2, this is AST2, ASC, M1 we already know, that is RBD square. We will need equation for M2, which is this, or total moment. Okay, so these equations are again very important from solving numericals or designing a doubly reinforced section. So please go through this derivation properly. Again, from exam point of view, you have this derivation which can be asked as a question of 10 marks. So you need to know this thoroughly, and also to solve numericals you need these equations. Thank you.